Hello students, this is Professor Chalai, and in this video we're going to look at the periodic variations in the various properties of the elements. As always, you can follow along with our Chapter 6 workbook. Now, in our last video, we talked about this idea of electron configuration, and typically we write them in this sort of fashion where we can summarize all of the previous electrons of lower energy as a noble gas, and then just write the electrons of the higher energies. And the reason why we only really care about the electrons of higher energies is because whenever we're doing chemistry, those are the electrons that are important. The electrons with lower energy don't really do anything. They just sort of sit there in the atom. So to talk about these various electrons, we often refer to them as either valence electrons or core electrons. And so the electrons with a higher energy in this sort of outermost shell of electrons are what we call the valence electrons. So the valence electrons are electrons in the outermost shell. We use the word outermost because they're actually furthest away from the nucleus of the atom. So electrons in the outermost shell, basically what that means is they have the highest n values, right? Outermost shell just means highest n values. On the other hand, core electrons are going to be all other electrons. So they're going to be electrons closer to the nucleus with lower n values, right? So we can use this to figure out valence electrons and core electrons. We just look at the highest n value for their different orbitals. The ones in the highest n values are the valence electrons. And I mentioned that because they're in the outermost, furthest from the nucleus, they actually are the ones that are able to do the most amount of chemistry. And to go about understanding why that is, we need to look at Coulombs' law, right? This is Coulombs' law written in a very simplified manner, where the force between two charged particles, so this is the force between two charged particles, depends on the force of the charge on one times the charge on the other. So we're calling them A and B. Charge, so Q is the charge in this case, charge and charge. So you multiply the charges on both of them divided by the distance between them squared. So let's say you have two charged particles, let's say a positive charge and a negative charge, some distance r between them, right? The force would be proportional to the charge on this one squared multiplied by the charge on the negative one squared divided by, not squared, sorry, I added extra squares there, divided by r squared. So this is the force between them. So as you can tell right away, if one's negative and one's positive, when you multiply them together, the force will be negative. If they're both the same charge, either they're both positive or they're both negative, the force will be positive. So negative force only happens when one's positive and one's negative, and a negative force is just an attractive force. Attractive. So if there's a negative force between two things, we'll pull it together. A positive force just means that it's repulsive. The two things will push each other away. Repulsive. There we go. And this is going to help us a lot in thinking about these different properties of elements. Because as we know, an atom, if we model it very crudely, we can think of it as having all of the positive force from all the protons in the center, and then the electrons are sort of surrounding the nucleus. The outermost electrons, right? Let's use this color. The outermost electrons, these are going to be the valence electrons. There we go, valence electrons. And the innermost electrons, these are the core electrons. And so because these valence electrons are the ones that are outermost, they're the ones readily available to do chemistry. And so there is going to be a force between this nucleus and this outermost electron, the valence electron. And it's that force between those two that we're going to be interested in. All right. But if you think about it, right, so the force, you can think of the force as being proportional to the charge of the nucleus, let's call that Z, that's times the, let's say, just the outermost electron, divided by the distance squared, right? But what about all of the electrons in between, right? So if the net positive force from the nucleus is pulling in the outer electrons, the valence electrons, the core electrons are trying to push it away. So from the point of view of these outer electrons, it's kind of like if the force that's coming from the nucleus is weakened by all of the core electrons. So instead of using the charge from the nucleus, we can change this to some weakened nuclear charge called the effective nuclear charge, Z effective. So the effective nuclear charge is just the charge from the nucleus screened or blocked by the core electrons. So if an atom has, let's say, a nuclear charge of, I don't know, 10 plus 10, right? It has 10 protons, so it has a charge of 10. But let's say there's two core electrons, then the Z effective will be the positive charge of the nucleus, but subtract out the two negative charge from the two core electrons, so the effective nuclear charge will only be plus 8 because it's screened. So that's going to help us think very much about these other properties that we're gonna talk about. So let's think about this equation. The force between the nucleus and the outermost electrons will depend on this effective nuclear charge and this distance between the nucleus and the outer electrons. So keep that in mind. It's going to be dependent on these two things, the effective nuclear charge and the distance between the nucleus and the outer electrons. So the first thing we're going to talk about is atomic radius, or sometimes called the covalent radius of the atom. And this is simply the effective size of the atom, right? A radius is just a way to measure the size of the atom. All right, well, let's see how the size of the atom changes as we go along the periodic table. And if we think of a periodic table, right, a general periodic table, we can think about how the size changes as we go across across a group. Does the cross have one S or two? I don't know. Or as we go down a period. Sorry, I mixed those up. Down a group, or as we go across a period. There we go. I knew something felt fishy. Okay, so let's think about how all of these different properties that we're going to talk about vary as we go across the period and vary as we go down the group. So as we go down the group, right, we know that we keep adding more and more shells around the atom. So if we think about our model, we're adding more and more shells, so this distance is getting larger and larger, right? So if R gets larger and larger, the force gets weaker and weaker. So the force is pulling in, well, we get larger and larger, so I think that makes it obvious, actually, that as we go down the group, we're adding more and more layers of electrons, and so the size of the atom, the atomic radius gets larger. So let's write that. The radius increases down a group for the simple fact that we're just adding more and more layers of electrons. But what happens when we go across a period? So when we're going across a period, we're not adding more and more layers. We're in the same layer. So the R value stays the same as we're more or less as we're going across a period. But what happens to the effective nuclear charge? Well, as we go across a group, let's look at let's look at this periodic table here. Let's look at as we're going across the second group here as an example. The number of core electrons in this case is always going to be 2, right? Everything else are going to be valence electrons. But the nuclear charge Z increases, right? It goes from 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the Z effective goes up because the nuclear charge goes up, but the core electrons stay the same. So as we go across the group, the Z effective goes up. The effective nuclear charge, the pull on the Z, yeah, I'll stop right there. The effective nuclear charge goes up. So what does that mean for the force? We know that the R stays the same more or less as we go across the group, the period, but Z effective goes up. So that means the force will go up. So the force pulling the electrons in goes up. So if the force pulls on electrons stronger, the atom is going to get smaller and smaller because the electrons are being more tightly pulled in. So generally then, what this means is that the radius decreases across a period, right? And so that's something we need to know. Let's look at the first ionization energy. So the first ionization energy is just the energy it takes to form a positive ion. So let's say you start with sodium. The first ionization energy is the energy it takes to separate that sodium ion from an electron by pulling it away. And the energy here will be the first ionization energy, 1 IE, sometimes written as IE1. Okay, so how can we understand the first ionization energy? Well, it's the energy it takes to rip an electron away. And so you might think, well, the weaker this force is, the easier it is to rip an electron away, right? And we just talked about how as we go across the period, Z effective goes up, and so it becomes harder, the force becomes larger as we go across the period, so it becomes harder and harder to rip an electron away from the atom. So let's write that. So the first ionization energy increases across a period. And so this is why it becomes harder and harder to form positive ions as we go down the periodic, across a period in the periodic table. That's why the metals form positive ions more easily than the non-metals, because it becomes harder and harder to do so. And why is that? Because the effective force that's pulling the outer electrons is becoming stronger. But what happens when you go down a group? Well, when you go down a group, the effective nuclear charge actually stays the same, but the radius increases, because as you go down the group, you're adding more and more layers of electrons. So if you're adding more and more layers, the radius R gets larger, and so if R gets larger in this equation, the force pulling the outer electrons gets weaker, right? So if the force is getting weaker, then it becomes easier to pull away an electron because the force is weaker. The force holding the electron back is weaker, so it becomes easier to pull an electron away. And so what then happens is the first ionization energy decreases, or it becomes easier to ionize down a group. All right, let's think about the opposite, electron affinity. Electron affinity is how easy it is to for the atom to attract an electron to itself, right? This is useful for when we want to form negative ions. That atom has to attract an electron to itself. So let's think about the force. The force, the stronger the force now, the easier it is to attract an electron to yourself, right? Because you're pulling on the electrons more strongly, so it's easier to attract it. Usually for attracting things, force, as I mentioned, was negative. So also the electron affinity will be negative typically when we attract electrons. So what I'm trying to say there is that as we go across the period and we know the force gets stronger, the electron affinity becomes easier, or I'll use the word decreases here because that means it becomes more negative. Because I mentioned that the attractive force is a negative one, so it becomes easier to attract an electron, but that just means it becomes more negative across a period. And similarly, as we go down a group, right, the force becomes weaker because the R value becomes larger because the atom size is becoming larger. And so the electron affinity increases, or it becomes harder to attract an electron. It becomes more positive down a group. And just to make this clear, it becomes easier, and for this one it becomes more difficult, just so that we don't confuse the sort of decreases and increases language. So far we're thinking about all of these different properties in terms of this force that the electron feel from the positive pull of the nucleus of the atom. So what does that mean for metallic and non-metallic properties? Well, we know that metallic elements tend to form positive ions and also tend to sort of form these sort of sea of delocalized electrons when they form bonds, right? And that happens because the electrons don't mind giving up, the atoms don't mind giving up their outermost electrons, and that's why they form sort of this sea. So to form the sea of electrons, really what we need elements to have is a weak pull on their electrons. That helps them to form positive charges, and that also helps them to form this metallic bonds with a sea of delocalized electrons. So what that means then is the weaker the force pulling on the outer electron, the more metallic it is. So basically, metallic properties will decrease across period, because we know as we go across a period, the effective nuclear charge gets stronger, so the pull becomes stronger, which is not good for metallic properties, but it's good for non-metallic properties. Non-metallic, MET, I did not spell that correctly. I'm not going to fill this one out. You can assume it's the opposite of this one. Okay. And as we go down a group, right, atom gets larger, the radius gets larger for the pull from the nucleus to the outer electrons, which means the force gets weaker. So metallic properties increases down a group. There we go. And this is why we typically, when we think of a periodic table, we think the ones over this side are more non-metallic, and the ones sort of over here are metallic, right? And the line is drawn somewhere over here. Sorry, let's draw this line there. There we go. All right, so that's how some of these properties vary as we go up across a period in a periodic table or down a group in a periodic table. And they can all be described by this Coulombs law as we focus on the force between the nucleus of an atom and the outermost electrons as determined by this effective nuclear charge, which is basically just the charge of the nucleus when it's screened out from the core electrons. All right, this will bring us all to the end of chapter 6. Here's a summary of all those things that we talked about previously. So it's right here for you to easily refer to. And at the end of this chapter, as with every chapter, right, there's a host of questions that you can practice on. If you have questions, please send me a message and I'll be happy to answer them. Otherwise, I will see you in the next chapter